Hey guys, Mr. Brown here, and this video is for Chapter 9 of the Klein Organic Chemistry text, and that chapter covers the alkynes and their chemistry. Here we see some of the defining characteristics of an alkyne, a molecule called an alkyne, and that is namely the carbon-carbon triple bond between two carbons in an alkyne molecule. The triple bond is formed by one sigma bond and two pi bonds. So in a triple bond, each of the carbons is sp hybridized, meaning they've only hybridized one of their s orbitals and one of their p orbitals, and they've left the two other p orbitals alone. Those p orbitals are half filled as we see when we hybridize carbons orbitals, and they will overlap. Each of those two unhybridized p orbitals we see here will overlap both above and below the nucleus and to either side of the nucleus on each of those carbons, resulting in one overlapping head-on sigma bond between their sp orbital and then two overlapping outside above and below p orbitals, giving us the total triple bond. The outside bonds shown here, so that would be probably a bond to hydrogen because that's an s orbital overlapping with carbon's sp orbital to give the final fourth bond to complete its octet rule. Because these sp orbitals must be stuck out side to side from one another, because we have the p orbitals in 90-degree configurations from one another, the two sp orbitals can only stick out from side to side because that's as far away as they can get from the p orbitals. Because of that, the triple bond is necessarily linear. All of those bond angles in the carbon-carbon triple bond and whatever is on the other side of the carbon-carbon triple bond must be really very close to 180 degrees for this all to work. And because of that, we don't really see triple bonds in rings unless we have rather large rings, and probably the smallest example is cyclononine, and it's still kind of unstable because of all of the ring strain that 180 degree bond angle would introduce if we try to put an alkyne into a ring. The simplest of the alkynes is much like our very simple alkene. Remember that I told you guys IUPAC would say that the correct name for the two-carbon alkene would be ethene, but all of the literature and regular chemists call it ethylene. Very similar, the simplest of the alkynes, the two-carbon triple bond alkyne, IUPAC would say that the common name, we'll see in a minute with the nomenclature, or the correct technical name rather, should be ethyne, and it is not. It is commonly called acetylene, and we've just kind of highlighted that here to go ahead and get you used to that. It may be even more ingrained than ethene. You will never hear the two-carbon alkyne be called ethyne. It will always be called acetylene. It's quite a common molecule. It's used a lot in welding and other high-temperature gas applications when you need a very hot flame, and so it's sold as acetylene, and everybody refers to it as acetylene, and you should refer to it as acetylene as well. On this slide, we have the rules for naming alkynes according to IUPAC nomenclature. We see that rule number one, much like we saw with the alkenes, we are going to replace the ANE ending with the YNE ending. And if there is a triple bond present, we're always going to make sure to include it in the longest chain. The triple bond gets the lowest locant regardless of the substituent. So as with the double bonds, a lot of times triple bonds can make naming easier because it makes it easy to pick which end of the carbon chain to go from. Just make sure you pick the end of the carbon chain closest to that triple bond. Don't forget to list the substituents, as always, alphabetically in order when naming. As a reminder, di, tri, tetra, neo, sec, and tert are not considered when naming or alphabetizing. Iso and cyclo are considered when alphabetizing. They're so common, I guess, for whatever reason. If you run into the extreme edge case where you need to alphabetize a complex substituent, the first letter of a complex substituent determines its alphabetization regardless of whether it's a prefix. So basically, it's di, tri, tetra do count when it's a complex substituent, but those are uncommon and probably don't need to keep that rule at the very top of mind. If there are double bonds and triple bonds, we probably will run into some of these cases. Always include both when determining the longest chain. Number from the end closest to either a double or a triple bond. And "-ine" always comes before "-eine" in the name, and that's simply due to the alphabetization status. We'll see some practice on the next slide. A few more notes about nomenclature on this slide before we practice a few. We see that small variants of acetylene are often just described by their attached substituents. We got a few examples here. We notice this first one. This is an acetylene molecule, but instead of a hydrogen on one end, that hydrogen has been replaced by a methyl group. So it would be not incorrect to call this one methyl acetylene. The next one, we have an example where the two hydrogens have been removed and replaced by two isopropyl groups. So we call that one diisopropyl acetylene. And then in the final example there, we have an example where a phenyl group is on one side, a propyl group is on the other side. We call it phenylpropyl because pH becomes before PR when alphabetizing. So the name, again, phenylpropyl acetylene. We also will be hearing a lot about the difference between terminal and internal alkynes through the rest of the text. And we show pictures of each of those here. When a triple bond is at the end of a molecule, or has a hydrogen on one end rather, it generally terminates the molecule there because it can only hold one other bond. So we call alkynes with hydrogens bonded to them terminal alkynes. When both sides have substituents, we call them internal alkynes, and we'll see again that terminology talked about through many of the reactions of alkynes. So here on this slide we have some nomenclature examples. We see in the first example there a chain of 1, 2, 3, 4, 5, 6 carbons with what looks like a methyl group down near the beginning. If we name from the correct end, we'll start down here because that is going to be closer to our methyl group. We can really start on either end according to the triple bond because both would put it in a 3 position, but starting from this end puts the methyl group in the 2 position. So this molecule is 2-methyl-3-hexyne. The next one is just a straight chain with a triple bond somewhere along the chain, no substituents or anything. If we count from this end, because that will put a 3 on our triple bond instead of a 5, we see 1, 2, 3, 4, 5, 6, 7, 8 carbons, making that 3-octyne. The next molecule, you can name a few different ways. If I was naming it, I would probably just call this one tert-butyl acetylene. We see this is an acetylene that's had one of its hydrogens replaced with our common tert-butyl group. It would not be incorrect either to call this 3,3-dimethyl-1-hexyne as well. The next molecule we would call 5-propyl-7-methyl-1-nonine. The chain that we count, we start down here at the triple bond, make it number 1 because that's as low as it can get. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's the longest carbon chain we can find in that molecule. That puts the 3-carbon propyl group on carbon number 5, a methyl group on carbon number 7. The next molecule we see there looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons as our longest carbon chain. And we see that the substituents are a ethyl group on 5, 2 methyl groups on carbon number 7, and we number from that direction starting here because that makes our triple bond a 3 instead of some other larger number, making this molecule 5-ethyl-7,7-dimethyl-3-decyne. The last molecule that we have to name down there is quite a long example. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is going to be a decine of some sort as well. We see an ethyl group on 8, a dimethyl substituents on what appears to be carbon number 4, and then we see 3 chlorine groups on carbon number 1. So putting that all together, we come up with 1, 1, 1, trichloro, 8 ethyl, 4, 4, dimethyl, 2 decine. And we put the chloros first because tri is not involved in alphabetization, and chloro comes before ethyl in alphabetical order. So we'll draw the last 2 examples down here. We see the first one is a 4,4-dimethyl 2-pentyne. So we'll start with drawing the 2-pentyne. We will do a carbon chain there, signifying. And so that is a total of 1, 2, 3, 4 carbons. We just need to add 1/5 one to make the decine. And on carbon number 4 here, we will put us a pair of methyl groups, giving us 4,4-dimethyl 2-pentyne. Now, the other example here says we want to do 3 ethyl, 2,5-dimethyl 3-heptyne. So when we draw that out, we would give us the heptyne. So 3-heptyne, we start on carbon 1, carbon 2, and then 3 would start our heptyne. So 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we'll put a 7th one down here. So that's a good example of 3-heptyne. 1, 2, 3, 4, 5, 6, 7 carbons to give us 3-heptyne. Number 5, 1, 2, 3, 4, 5 has an ethyl group. And 5 also has a methyl group. And 2 is a methyl group as well. So that is the depiction of 5-ethyl, 2,5-methyl, 2,5-dimethyl, 3-heptyne. Before jumping feet first into discussing the reactions of alkynes, we're going to point out one of their most significant characteristics, and that is that they are a bit easier to deprotonate than other alkyl or alkenyl groups. So that hydrogen, the proton on the end of a terminal alkyne specifically, because if it has one hydrogen, it is terminal, is easier to remove than, say, the hydrogen at the end of the butane molecule that we see in the top here. We see that bases such as NaNH2, sodium amide, and sodium hydride can deprotonate the terminal alkyne proton. Those will not work for things like a butane group or something like that. And while they are very, very reactive species, they are kind of off-the-shelf products, if you will. You can go to your chemical supply and order sodium amide, NaNH2, and they can send it to you in a bottle. Whereas if you want to deprotonate butane, you got to do a lot of kind of heavy in-lab chemistry to make that happen. And so alkynes give us this ease of deprotonation that allows us to use that lone pair. Now that we have a lone pair on a carbon atom, that's the first stable carbanion that we've run into yet, and we can start using that carbon as a nucleophile in different reactions, which gives us some flexibility in what kind of chemical reactions we can do. And of course, we'll be looking at that as we go forward through the chapter. On this slide, we see a little bit of an explanation why those protons are so much easier to remove than those in other double bond sp2 and sp3 carbon situations, and it's due to the shape of the sp orbital itself. The sp orbital, as its name implies, is only made of one s and one p. It's made by the combination of one s and one p being mixed together and hybridized, which means when you compare it to an sp3 and an sp2, they're more lobular, like the p orbitals, because they incorporate more of the p orbitals, whereas the sp is very spherical and it holds those electrons, that lone pair of negative electrons, much closer to the positive nucleus because of its more spherical shape. It stabilizes a lone pair, it stabilizes a negative charge better that way, and that's why it's easier for it to give up that positively charged proton than the other two cases. So on this slide, we're asked, will each of these substances deprotonate the terminal alkyne? And we're basically just needing to refer back up to the pKa chart from the last page, and we see that sodium amide and sodium hydride are bases that are strong enough they can deprotonate the hydrogen atom here in this place. And so in both of these cases, A and B, we would see that the NH2 ion specifically would be able to deprotonate that hydrogen, and the two electrons would be donated there in that case, forming an acetanilide ion. In this case, this actually forms sodium hydride, dissociates in solvent to give us hydride ions, which are dissimilar from protons. They're a hydrogen that has both electrons. Rather than a bare proton hydrogen nucleus, this is a hydride ion that has a full pair of electrons in that 1s orbital. That hydride ion can bind the proton there, leave the electrons in the bond, forming an acetanilide ion, and also some H2 gas. In the final example there, if we go back and look, we see that the oxygen bases are typically not strong enough to deprotonate the terminal alkyne, so we would not expect that to lead to formation of any products. I've included a video here in the slide that you can look at for yourself. I won't sit here and watch it with you, but this gives you some look into what sodium amide is. The guy goes through both how it's formed and then some of its behaviors. He doesn't show it deprotonating an alkyne, but he shows some of its behaviors when it's mixed with acid, water, some oxidizers and stuff like that. It's kind of a neat video. Some of the techniques may not be recommended, but it's a pretty good watch. So if you want some background as to what sodium amide looks like and how it actually behaves in the lab, go through and give that a watch. So if you did or do watch the video from the previous slide, you will have a good basis as to what sodium amide is and how it's formed. And now we'll also say that it's very often used in the preparation of alkynes. And so dihaloalkenes, how do we get alkynes in the laboratory? We take dihaloalkanes, and these are alkanes that have two halogens on them. And it's important to note these can be either geminal or vicinal halogens, meaning we have two halogens on the same carbon, or two halogens on carbons that are bonded together. So two successive carbons, you might say. If with this setup, you can treat the dihalide with sodium amide or other examples of strong bases, but sodium amide is used very often for this purpose. And so the sodium amide will force two E2 elimination style reactions to give us two new pi bonds and affording a triple bonded molecule. We just learned in the previous slide that sodium amide is also a strong enough base to deprotonate the formed alkyne itself. So what we very often see in these reactions when we're making alkynes, we'll treat a dihalide with NaNH2, and the reaction will go so far that we end up with the alkylate ion. And we can easily put that hydrogen back on by just throwing some water in our flask. That alkylate ion is a strong, very much strong enough base to remove a hydrogen from a water molecule and reprotonate itself. So that's really how we just kind of take care of that. Here we see the E2 mechanism. We should be familiar with this mechanism already, where we have proton removal, the pair of electrons that was shared in the bonds between the proton and the carbon atom is moved over to form a pi bond, and then loss of a leaving group allows for the adjacent carbon to still have a correct octet. This just simply happens twice for the alkyne product to be made. We just make sure we put enough base into our reaction flask that, and we just wait, and a strong enough base, such as sodium amide, will take both protons away from that carbon, causing both of the halogens in the dialkyl halide to be lost as leaving groups, giving us the formation of two new pi bonds, giving us a triple bond. So we're going to do some examples here and see if we can draw the two successive E2 mechanisms for the following transformation. So in example 1, or example A rather, maybe, we see that we have this dibromo compound being reacted with NaNH2. And so our base, draw our dibromo compound, 2 BRs. Our base is going to be the amide ion, which has that structure. This carbon here has 3 implied hydrogens, and typically if the result of the reaction can be a terminal alkyne, that is the direction that the triple bond will typically be formed. In this case, we are forced to have a terminal alkyne because that is the only place that we have any beta protons. And remember, E2 reactions require beta protons to move forward. So we will have proton transfer. This pair of electrons in that bond will move down there. And the first part of the reaction, or the first elimination reaction rather, gives us this product. Show my loss of I didn't show my loss of the leaving group, and show the loss of the leaving group there. Then another, and I'll come down here and redraw that, show the second elimination. Leaving so like we said, we made sure to put enough sodium amide in our flask such that we have plenty to react with those beta hydrogens. We will see a second E2 reaction. Loss of the leaving group, proton transfer, loss of the leaving group. And now we see the terminal alkyne product. Because we have excess NaNH2, another amide ion present in our reaction flask would more than likely come in finally take that guy. There's no loss of a leaving group to accommodate that lone pair of electrons, but no new bonds are formed, so that carbon atom simply becomes a carbon ion with a lone pair of electrons there. And then finally, to reprotonate, we see that water is added. We will remove one of the protons from water, leaving a lone pair with the oxygen, giving us our reprotonated species. So we also have some hydroxide ions, and that makes sense because we learned that the oxygen bases are not strong enough to remove that proton, so it makes sense that water will donate that proton back to make the reprotonated version of our alkyne. That was example one. We saw how that works with a example where the halogens are on the same carbon. Now we'll look at example 2 where the halogens are on adjacent carbons. And so we will I'll redraw the species here. And I will draw the implied hydrogens as well because those are what are going to be lost when we form our triple bond. So again, we react with the amide molecule, and this time I'm just going to so we see proton transfer, loss of a leaving group to give us our first E2 elimination. We still have a chlorine there. Redraw that over here, maybe a little bit better, maybe. Nope, I don't believe so. Another base ion moves in, another proton transfer, another loss of a leaving group. Leaves us with the same molecule that we had in the previous step. And so I think you can figure out what the next steps are for this mechanism. We use a base ion to remove the last proton, and then during workup we use water to add the proton back to get the end of the reaction or the product of the reaction that we want. Now that we can form alkynes, let's start looking at some of the reactions that we can do to them to get new and interesting products from alkynes. The first and perhaps most simple thing we can do to an alkyne is hydrogenate it. We can add hydrogen to the triple bond to afford either an alkene or an alkyne product. When we use catalytic hydrogenation, which adds hydrogen gas, we bubble H2 through a solution containing our molecule and some platinum as a catalyst. Usually the platinum is embedded on something non-reactive like carbon. So we have like solid carbon, we have some platinum, literal platinum metal embedded in microstructures in that carbon, and we mix that all with our alkyne that we want to react with and bubble some hydrogen gas through the mixture. The hydrogen gas, because of the platinum catalyst, will react with the triple bond to give two hydrogens. Will add an H2, will add one time to give an alkene, and then add to the alkene a second time to give the alkane. In fact, you can't use pure platinum catalyst if you want to stop at the alkene. If you want to stop at the alkene, you have to use what's known as a poison catalyst. So some of these, it's called Lin-Lars in some cases, and it might be indicated by a nickel compound. So sometimes we use nickel instead of platinum in place because nickel is not quite as good as catalytically as platinum is, and because of that we can stop at the alkene product instead of moving all the way to the alkane product. In catalytic hydrogenation, we always get, if we use a poison catalyst and we stop at the alkene product, we always get the cis alkene product, and this is because the mechanism of the reaction has the H2 add to the same face of the double bond. So you cannot form the trans isomers of those alkenes from catalytic hydrogenation. You have to use another method that we'll look at momentarily. So we have some quick predict the products examples here on hydrogenations of some example alkynes. And in the first box we see two examples, and both of these examples list nickel in the reactants. We're going to assume that both of those processes are employing a poison catalyst because of that nickel designation, and because of that we're going to expect the alkene product. And when we have alkene products from poison catalyst, that is going to be a cis alkene product, not a trans alkene product. So in the third example down here, that also says Lin-Lars catalyst, which will also have the stop at the alkene designation. It will also be a cis alkene, so that would be the product of that reaction. And then finally, in the last one, we see just pure platinum catalyst, meaning that molecule is going to go all the way to the alkane. So it is reduced all the way to sp3 carbons, and that is the result of that reaction. So if you have an internal alkyne and you want to reduce it to the trans alkene, there is a type of reaction you can do called a dissolving metal reduction. To do this reaction, you take sodium metal and dissolve it in liquid ammonia, and a radical reaction happens from the electrons that are actually solvated away from the sodium by the ammonia. Be careful, it's easy to confuse NaNH2 in ammonia versus Na in ammonia. NaNH2 is used to produce alkynes from dihalides and to produce the acetanilide ion from an alkyne, whereas the Na plain sodium in ammonia is used to go from an alkyne to a trans alkene. So, and notice this gives us the trans product. If we don't want the cis product, we don't do the catalytic hydrogenation, we do the dissolving metal reduction instead. So I posted another video, and again the link for these I'll let you find down in the course on the Moodle site. This is Nile Red actually preparing that solvent system that we just discussed on that last slide. He dissolves some sodium into ammonia. He actually does lithium as well. He shows how he makes liquid, or how he makes liquid ammonia, and then dissolves some sodium and some lithium in it. The color that you see from the solvated electrons is really neat, and everybody always kind of makes a big deal out of it. It is a pretty fun video to watch, so go over there and check that out when you have the opportunity. So we have some more kind of simple examples here. What happens when each of these is treated with the dissolving metal reduction, essentially. And all we have to do is take those alkynes that we see and turn them into transalkenes. And so we will show the first one here. We see that one, and then the triple bond is there. And then we have one more bond on that side. For the next molecule, we have, and then the triple bond is there. We go up, and we see that there are some bonds there and some bonds there. So that would be the result of a dissolving metal reduction forming the transalkene from that alkyne. The next one we see there, we would draw our cyclopentyl group. Maybe a little bit better than I did. Maybe. And then that would be the result of that dissolving metal reduction. And then this final dicyclobutane acetylene, odd molecule, but regardless, we can draw some squares with a transalkene in between. Draw another square to give the transalkene product of the dissolving metal reduction of dicyclobutane acetylene. Here on this slide is just a look at all of the routes of hydrogenation. We can take an alkyne through to the alkenes and the different routes of hydrogenation of those alkenes all the way down to the final alkane. Stuff like this is useful for when you're planning long synthesis of stuff. You can remember back to how to transform these groups in different ways. So here we have on this slide some examples of picking the appropriate reagent to get the alkyne to form the alkene that is displayed. And in the top example, we go from an alkyne to a cis-alkene, and we know that that comes from catalytic hydrogenation. So the reactants there would probably be something like H2 over Lindlar's catalyst, which is the nickel platinum catalyst. So maybe like Ni2B with some platinum or something like that. Just some nickel shown there somehow to show that we're not using the pure platinum catalyst. The next two examples are giving us transalkenes, so both of those would want to be done using a dissolving metal reduction, and we might show something like sodium being dissolved in NH3. Lithium might work as well, but it's easier to do with sodium. So sodium's our usual culprit for both of those transformations. And then the final example, we go from the alkyne all the way down to the alkane. So that is done with hydrogen over a platinum catalyst. And that is how we predict the hydrogenation products. The next reaction we come to is hydrohalogenation. So when we treat alkynes with HX, HCl or HBr or HI, we add Cl or Br or I to one of the carbons in the triple bond, and we do so in a Markovnikov fashion, meaning it adds to the more highly substituted end of the triple bond. If we use enough of the HCl or the HBr or HI, then two halogens are added to that carbon, completely eliminating any of the pi bonds, and both of those end up on that same carbon, so it results in a geminal dihalide. As with the alkynes, if you use some peroxides to kind of contaminate the reaction, you can use HBr and you can get a non-Markovnikov product. However, it's not that useful of a reaction because you can't control whether you get E or Z isomers and the products end up a mixture of both. And so unless you want a particular reaction mixture, which is not usually the case, it's a curious but perhaps not very useful reaction. So here on this slide we have some examples of alkynes being treated with reagents, as well as some dihalides being treated with reagents, and we're going to see if we can figure out the products. In the first example, we learned that when we treat alkynes with hydrogen halides such as HBr, HCl, HI, then the hydrogen halide adds to the double bond in a Markovnikov fashion, the triple bond in a Markovnikov fashion. And if we have enough of the stuff, two additions take place, affording us dihalides. In the second example there, we see a dihalide being treated with NaNH2. So in the first step, we would see two elimination reactions that would eventually end up stripping off even the final proton from the formed alkyne. But we do see that the second step is a workup with water, and so that will give us eventually the neutral alkyne products with a hydrogen on the end there. In the third example, again, excess HBr is going to add in a Markovnikov fashion to give us a dibromo product. In the third example, we treat a dihalide with excess NaNH2 and NH3 followed by a workup with water, and so we would expect to see in this case, the benzene ring with phenylacetylene is our product from that reaction. In the fourth reaction there, the first two steps would have us arrive at this product here. It's the same thing. Even though one has chlorine and one has bromine, that doesn't really matter. They're both halogens. They would both undergo two successive E2 reactions followed by a final proton transfer, and then the workup with water gives us the phenylacetylene product. However, we have a third step this time, and we see that this phenylacetylene product is treated with HBr that's been contaminated with peroxides, and so we're going to see a non-Markovnikov addition of bromine to the end of that molecule, and we're going to see we would see both trans and cis isomers of that molecule. So it wouldn't really be that, again, functional of a reaction, but it would be the case that that would be our products from the fourth reaction. And then finally, in the fifth one, again, we would make the phenylacetylene intermediate, if you will. It's not really, it's a reaction intermediate for us. And then when we treat the phenylacetylene with excess HBr in the final step, we finally just remake the geminal dihalide. However, we have replaced the chlorines with bromines. So the next reaction type we're going to look at is acid catalyzed hydration. When you treat an alkyne with sulfuric acid and water, just like with an alkene, you add water to the pi bond. You add OH on one side and a regular H on the other side, and the pi bond goes away. A few differences between alkynes and alkenes is that for an alkyne, first of all, it's kind of a slow reaction, so we need mercury sulfate as a catalyst, and that speeds it up to reasonable rates by way of a mercurinium ion. Second, when you add the OH and the H to an alkyne, there's still a pi bond there after the reaction takes place between the alpha and a beta carbon, if you will. That is what is known when you have a hydroxyl group bonded to an sp2 carbon. That's what's known as an enol. You see it up here. We have an alcohol group beside an alkene. That's why it's called an enol. Those are impossible to isolate because they quickly tautomerize. They react to form another isomer of themselves. In fact, what really happens if you kind of look at the transformation here, the hydrogen on the hydroxyl group is moved from the oxygen down to the carbon down here. And in effect, the pi bond is moved from between the two carbons to the carbon and the oxygen. And it makes sense because oxygen is so electronegative, it makes more sense for it to have the double bond than the other way around. So even if enols are reaction products, they almost never stick around. They require a acid or a base to catalyze. This transformation requires an acid or a base, but it literally only requires one molecule of acid or base. So it's kind of, in practice, impossible for this transformation not to take place. So when we react a alkyne with sulfuric acid and water, the result is not an alcohol or the enol as structured. The enol quickly tautomerizes to give us a ketone. And so what happens is basically the ketone is added in Markovnikov fashion. You can almost think of it as like a double bonded O being added in Markovnikov fashion to the triple bond, and the triple bond disappears completely. Interior, because of this, on a terminal alkyne where you have a hydrogen hanging off the end, you always end up with a methyl ketone. And so that can be a useful reaction. However, for interior alkynes, you can't predict which side is actually the Markovnikov side because they're both as substituted. And so you end up with mixtures of products. So it might not be that useful of a reaction unless you specifically want some methyl ketone, meaning a double bonded O with a terminal methyl group on one side and some big long chain on the other side. So here's a look at the so-called keto-enol tautomerization, a little bit closer look at it, at its mechanisms. Like I said, it's kind of impossible to prevent because it can be catalyzed by either a single molecule of acid or a single molecule of base, and it takes place very quickly. So we can't really isolate enols. There's been some work to do so in tiny molecular cages and stuff like that, some really kind of high-level chemistry, but in a typical lab, you cannot isolate an enol because even one molecule of acid or one molecule of base will cause all of an enol present to undergo the following tautomerization. So in the tautomerization, basically, like I said, a couple of proton transfers allows us to move the proton on the alcohol group down to the carbon instead. It's not really that proton in particular that moves, but it's done by way of either an acid or a base catalyst. A couple of proton transfers shuffles the proton from the oxygen down to the carbon so that the oxygen can have the double bond and not the carbon. Again, making sense because oxygen has the electronegativity. So we have some examples here. We are supposed to draw the products of acid catalyzed hydration of each of the following molecules. We can see that the top two molecules are alkynes, or terminal alkynes rather. So they are going to result in methyl ketones. We would see, if we followed the reaction really close, we would have an OH group installed here, and one of the pi bonds would disappear. That would give us that enol structure that we know tautomerizes in the presence of even minute amount of acid or base. We can't really clean our glassware of all acid or base completely, so we can't stop the tautomerization. So we would be afforded a methyl ketone product. So we would have the cyclopentane or cyclopentyl group there. We have some 1, 2, 3, 4, 5 carbons in the chain. 1, 2, 3, 4, 5 carbons in the chain. And on the Markovnikov carbon, we'd have a double bonded oxygen. And this is a methyl ketone because for reference, this is the ketone group. Anytime you have carbonyl carbon double bonded to oxygen, we call it a ketone as long as there's not a hydrogen or an OH or another oxygen bonded. And this, of course, is a methyl group here, so that's a methyl ketone. The next reactant there would also give us a methyl ketone. We would see the oxygen bonded to the Markovnikov position and the rest of the molecule as follows. The next two examples down there are internal alkynes, and so they are going to give us products that install an OH here or here and then tautomerize. And so in this example here, we're going to get some mixed products. We're going to have, there's 1, 2, 3, 4, 5, 6, 7, 8 carbons in this chain. So if we draw us a 1, 2, 3, 4, 5, 6, 7, 8 carbon chain, a couple of 8 carbon chains, 1, 2, 3, 4, 5, 6, 7, 8 carbon chains. In one of the products, we should have a double bond O on the third carbon, and in another one, we should have it on the fourth carbon. So one of our products would look like this, and one of our products would look like that. And so that might not be a very useful reaction because we would get a mixture of reactant products. However, we notice on the next example, we do the same thing. We would get a mixture of products, but due to the fact that that is a symmetrical molecule, we would see only one product, and that might be a more useful reactant for us. So 1, 2, 3, 4, 5, 6, 7, 8 molecules in the main chain. 1, 2, 3, 4, 5, 6, 7, 8 molecules in the main chain. We have methyl groups on either end. So that would be the one single reactant of that acid catalyzed hydration. So the next reaction we'll look at is hydroboration oxidation. This is a way to add that double bonded, that carbonyl O, to the other end, the non-Markovnikov end of the molecule. We saw the same thing with the alkenes using BH3, but in the case with the alkynes, we use bulkier analogs of BH3 rather. So some of the H's have been replaced with alkyl groups. You can see up here in these examples in diisomylborane and something called 9-BBN, which has this kind of really bulky dual ring structure on the bottom of it. And what that does is it prevents it. It allows it to undergo the reaction one time, but prevents it from doing it again. And so we don't get multiple additions to that alkyne. You don't get multiple hydroxyl groups on there. The keto-enol tautomerization still occurs. However, when you do this one on a terminal alkyne, because it adds on the non-Markovnikov side, the result is an aldehyde instead of a ketone. And so there's not a methyl group on that side. There's only a hydrogen on the end of the molecule now. And that's the difference between the sulfuric acid hydration versus the hydroboration hydration. So it follows, we have some examples of the hydroborations, and we probably can guess that in each one of these examples we would end up with aldehydes for these terminal alkynes that we see in the first two reaction examples. And so to draw those products, it would look something like this. with a hydrogen on the end there and double bonded oxygen on the third carbon. In that next example, we would have hydrogen on the end with a double bonded oxygen here. With the same structure there on the end. In our last example down there, we would simply delete one of the double bonds and have a double bonded oxygen in place. And we notice that that's a symmetrical molecule as well, so even if we add the oxygen to either side, we still get the same result. We still get the same molecule, so that's all one product there. So just a quick look back there, we can control the regiochemistry of hydrating a terminal alkyne. If we want the methyl ketone, we go the sulfuric acid, water, mercury sulfate route. If we want the aldehyde, we go with the substituted boron trihydride route. Another reaction that alkynes can undergo is halogenation. If you treat an alkyne with Cl2, Br2 in a solvent like carbon tetrachloride, that's the solvent here in this part of the reaction. We dissolve our alkyne in some carbon tetrachloride and then bubble some bromine or chlorine gas through that solution. We get tetra-substituted haloalkanes. That's not really, it's not well understood, even in today's chemical science. It's thought to undergo a lot of radical reactions to get to that product, but you get about 60-70% fully tetra-substituted alkanes. Now, in some cases, really controlled reaction conditions, if you only put one equivalent in, meaning exact number of mole to mole quantities of your alkyne to your Br2 or your Cl2, you can get you can't stop at the alkene di-substituted product, but still you get a mixture. You get anti-addition, but you get a mixture of E and Z products. So unless you have a way to separate those, it might not be that useful of a reaction. Our next reaction that we'll talk about is ozonolysis, and this might be one of the first examples of a reaction that helps us break a carbon chain. So we can see that when you take an alkyne and you treat it with ozone, which is an O3 molecule, so you have a solvent with your alkyne dissolved in it and you bubble ozone through that solution, the ozone will cleave the triple bond, oxidative cleavage, meaning it will break that triple bond and insert oxygens on those carbons that share the triple bond. After you kind of see, you get one double bonded oxygen and you get one single bonded oxygen, and that oxygen has a negative charge until you treat it with water to reprotonate it, and you get carboxylic acid products. So the R here is this R here. The double bond, or the triple bond rather, has been cleaved and replaced with a double bonded O and a hydroxyl group. And anytime you see this structure, we call that a carboxylic acid. If you do this process on a terminal alkyne, the final carbon here is completely oxidized. That is completely stripped away, and it gets, instead of becoming a carboxylic acid with COOH, it becomes carbon dioxide, C double bond O, C double bond O. And at last we come back around to that alkanide ion, which affords us perhaps one of the most useful reactions that we've studied yet in organic chemistry, and that is a way to lengthen carbon chains. So that alkanide ion that's made by stripping that last proton from a terminal alkyne can be used as a nucleophile in a substitution reaction with a primary alkyl halide. And it can be any primary alkyl halide. You can be a primary alkyl halide with a chlorine atom on the end of a 9 or 10 carbon chain. And you can get those two to react together, and in the process you will add that chain to the end of the alkanide ion. So this is the first reaction that we have that allows us to lengthen our carbon chains. And all we have to do is treat an alkyne with the sodium amide, the NaNH2, and then we react the resulting alkyne ion no longer with water, we treat it with some alkyl halide. In this example here, we treat it with ethyl iodide, so carbon filled out with hydrogens bonded to an iodine, and we can see that we add an ethyl group to the end of our carbon chain there. This is called alkylation of terminal alkynes, and again, probably one of the most useful reactions we've learned so far. We'll see some examples of how to put it into practice in the next couple of slides.